Hello students, in our last video we learned an important expression for continuity equation for one-dimensional unsteady unsaturated flow in porous media, and if you recall we said that rate change of soil moisture content with respect to time plus change rate change of uh, flow flux with respect to depth is equal to 0. And in this video, we are going to discuss another important fundamental expression which we call as Richard's equation, which is widely used to understand the rate of infiltration through different soil strata. But to do that, we need to understand the Darcy's law first. And Darcy's law says that if we have to measure this quantity Q is directly proportional to the gradient of head that exists in the porous media under consideration. Now, as we discussed, that soil is a porous media, so we would have soil particles, and in between them there is going to be voids. These voids could be occupied by air or these could be occupied by water. So whenever this water is flowing through that, of course it would widely depend that what is the characteristics of soil or how conducive the soil is to let this water flow. And hence, when we replace this sign of proportionality with constant of proportionality, we introduce a term that takes care of this conduciveness, which we call as the hydraulic conductivity. And this hydraulic conductivity typically has the unit of velocity and written as mm per second or meter per day and so on. Now let's focus on SF. As I mentioned, SF is the rate of change of gradient with respect to depth or with respect to length. So we can say that this SF is H2 minus H1 divided by Z2 minus Z1, where we will follow the convention that in upward direction Z is positive and in downward direction RZ is going to be negative. Now with this sign convention and ensuring that flow only takes place from the point of higher elevation to lower elevation, because if we remove all the other heads and assume that this flow is taking only through the action of gravity, we know that from higher elevation water will always flow through lower elevation. But if you simply see this formula, that sign convention is not taken care of. So we will say that instead of just writing it as KSF, Q and will be written as minus of K H2 minus H1 divided by Z2 minus Z1, and this will ensure that we are accounting for the fundamental physics that flow can only take place from points of higher elevation to lower elevation. In compact form, we again write this as minus K del H upon del Z. Now, an important question arises how we are going to take care of this height h. To understand this h, we are going to express all the head h of water in terms of height. If you recall, the same kind of convention was used when we tried to write Bernoulli's equation, and this expression of head of water in units of dimensions of height also means that we are expressing h as energy per unit weight of water, and hence we can write this total head comprises of pressure head plus velocity head, and we should divide it by gamma because it has to be energy per unit weight, plus the head because of its datum above some by virtue of its position above certain reference point. Now when we are talking about unsaturated soil, and this unsaturated soil is closer to the surface, and we can always assume that the water that is present in pores of this unsaturated soil is at atmospheric pressure, and we can always set reference atmospheric pressure to 0. So we end up with the term of pressure because of atmosphere plus pore pressure, because here we have some water, here we have some air is already at atmospheric pressure, so there would be some water molecules that are also going to exist some pressure, so we can reduce this term to 0, but we are still left with the pore pressure plus v square by 2g plus z. Now, when we are talking about flow through subsurfaces, the velocity is just taking place in form of a trickling in a typical case. So we can safely assume that the velocity is closer to 0, and when we take it square, that quantity further reduces. So the total head in the unsaturated soil near the strata or surface essentially comprises of pore pressure plus the datum. Now, as we took the convention that Z is positive upwards and negative downwards, if we take the ground strata, something like this, that means that as the water is entering into the surface, so if rain has happened just now and water starts trickling, that means that this Z is always going to be negative because we are interested to understand how water is penetrating in the downward Z direction. So by convention, our Z is always going to be negative. Now, let us also look into another term which we are borrowing from the understanding of soil mechanics. Pore pressure in unsaturated soil is always negative because we can interpret this pore pressure as the suction force, pore pressure as the suction force which resists the flow of water away from it. Now, this pore pressure or the suction force generally has two components. One we call as metric suction and another we call as osmotic suction. Osmotic suction typically develops in the soil which have high salinity. But for sake of simplification, in the context of hydrology, we would assume that our metric suction or the suction because which is getting set up because of the capillary action. Because if there is a particle of soil, this that would have tendency to hold water molecules closer to it, as a result of which void of air gets created surrounding these soil particles, and depending upon strength of this suction, this creation of void results in an entry point of moisture or facilitate the creation of a head that would be exactly equivalent to flow happening from higher elevation to lower elevation. So we would typically deal with metric suction, and by default this is taken as negative because we also say that this is in unsaturated soil, this pore pressure is always negative, and we mentioned that our datum are in downward direction. If we take ground level as reference, our Z is also going to be negative, and hence total head can be written as minus phi and minus Z and their summation. So if we know total head, we can determine and the depth below a surface, that is Z, we can always determine what is the section head that is developing. Also, let us try to focus a little bit more on this term phi. Let us say that we are in a soil strata, and assuming all other properties like density, conductivity remain same, we have at point 1, we have value of suction as minus 50 centimeter. We would be always expressing all pressures, all datums, of course, in terms of height. So this suction is represented as in the units of centimeter. If you go to soil mechanics, this suction is typically represented in the units of pressure, which is kPa or MPa. But we will not worry about that because you can always go from one dimension to another by dividing or multiplying by weight of water under consideration. Now, if we look at point 2, our suction is minus 65 centimeter. That would mean that if we focus on particle 1 and particle 2, tendency of particle 2 to hold water is stronger in comparison to particle 1. And if we invert the situation, that is, now particle 2 here has suction head of minus 65 and particle 1 has suction head of minus 50 centimeter, that would mean that this has a stronger suction in comparison to the point here, which is going to have a weaker suction. That would mean if there is a drop of water here, it would have a tendency to flow towards a particle which is going to have a stronger suction. Now, gravity would act into exactly downward direction. So we say that hydrostatic condition would be reached where suction force is equal to gravitational force. And whenever there is a disbalance, we would have net acceleration of particle, or there would be some fluxes that would get set up either in upward direction or downward direction, And with help of a numerical, we will try to understand how to uh, develop the soil moisture profile in unsaturated soil bed. So let us say that we have a soil strata in which we mark these 2 points. Now this point 1 is at depth of 0.8 meter from the surface, and point 2 is at 1.8 meter below the soil surface. We put some piezometers and we measure that the total head here is minus 145 centimeter, and the total head here is equal to minus 230 centimeter. We were asked to calculate what is the net soil moisture flux that is taking place between point 1 and point 2, and there are two important things that we have to account for, that what is the magnitude and of course what is the sign of flow, because if you invert the sign then you can confuse evaporation for precipitation, and that is going to be a blunder from hydrological modeling perspective. Now if we look at this, so once we have taken care of this sign and magnitude, we recall that our Q is equal to minus K SF, or this further can be written as del H upon del Z, or minus K H2 minus H1 Z2 minus Z1. Now, since we would be developing multiple profiles, so it's always better to write the values of all the terms that are involved. So our K in this case can be taken as 0.0484 centimeter per day. So this is a constant that would be generally available, and we will also discuss how it is related to the metric suction. Then H2 in this case is given as minus 230 centimeter, corresponding to Z2 of minus 180 centimeter, because this is 1.8 meter. H1 is equal to minus 145 centimeter, and Z1 is given as minus 80 centimeter. And when we write this expression, we can say that our Q is equal to minus K minus 180 plus 80, because this is one negative sign here also. And so on in numerator we should have H2 and H1, sorry. So this should be minus 230 plus 145, and here we are going to have minus 180 plus 80, and after substituting the values we get the value of Q as minus 0.0412 centimeter per day. Now there are multiple things that we should notice. There is a negative sign that is intact after substituting all the values. That clearly means that the direction of flux is in downward direction. That means now infiltration is taking place, and that would mean that the available soil moisture has resulted in creation of heads in a way that water is going from the layers on the top towards the downward layer, which indicates that precipitation might have occurred just an instance before, or it is happening right now. And similarly, as the time changes, because in summers versus winters the condition of soil or the available heads H1 and H2, they are going to be different, we get a profile that how Q is varying with respect to time, and we typically end up with plotting time series. Another important thing here is that you should notice that we are given total heads. So if we just take a difference of H2 and H1, it comes out to be 85 centimeter, whereas the difference of elevation between them is 100 centimeter. So that would mean that the suction pressure, or the pore water pressure, which is acting with negative sign, that is reducing the effective head that is available purely because of gravity. Because if you just consider these two soil particles at 1 and 2, the elevation difference is 100 centimeter. Now, instead of using this term as 100 centimeter over whatever difference of 100 centimeter, there is some compromise that has been made to this head that is available, which is now 85 centimeter. That means the soil here, the water here wants to go in this direction because of gravity, but the soil particle which is at depth 1 has more suction in comparison to the soil particle at depth 2, and hence it is trying to hold the water towards it, as a result of which there is a net drop in available head to that is going to facilitate the flow in unsaturated porous media. Now that we have understood our H is equal to 5 plus Z and our Q can be written as minus K del of 5 plus Z divided by del Z and del theta upon del T is equal to minus of del Q upon del Z, we will combine 1, 2 and 3 to arrive at our famous Richards equation. So what we can do here, we can write this expression of Q as minus K del phi upon del theta into del theta upon del Z plus K, because when you solve it and applying chain rule, and we will keep this negative sign outside. We will keep this negative sign outside and everything can come here. So basically what we did, we applied a chain rule here. And this term, when we combined, that is rate change of phi with respect to theta, because as I said, suction also changes as the soil moisture changes or the conductivity changes. We can write this term as another constant d into del phi upon del z, negative sign remaining outside, plus k, because this k got, because the derivation of z with respect to z would be unity and the constant k is already present. Now if we take the derivation of del q with respect to z again, derivative again, we end up with the expression minus del upon del z d into del theta upon del z plus k. And we know that from continuity equation, this del q upon del z is equal to minus del theta upon del t. So if we equate these two sides, we end up with an expression d into del theta upon del z plus k. Both these negative sign cancels out. So del theta upon del t is equal to del z d into del theta del z plus k. And you clearly see that if we want to understand that at what rate soil moisture content is changing, all the terms in this equation are now expressed in terms of theta, and we have gone away from measuring suction, and this equation is typically known as Richards equation. You can see that solving this equation is not going to be that easy without making some simplifications, that what is the fate of d, how k is varying with respect to theta, and so on. So different solutions, specifically approximate solutions, are proposed for this equation, and we will talk about the final forms of these approximate solution in our discussions on infiltration. Thank you.